Hello there, everyone. So this is the first and only video of section 2.4. In this section, we're going to introduce block matrices, and then we're sort of going to go through the usual progression. When we introduce something new, we'll do some addition, multiplication, and a couple examples. So what we're going to do is very, very useful a lot of times in applications, but also throughout some things we're eventually going to define. It'll be useful to define matrices in the way we're about to show. You can sometimes define them. So, a block matrix, sometimes also called a partitioned matrix, is a matrix whose entries are defined as smaller submatrices. And so here, submatrices, we're just defining its entries as smaller matrices. So, what this is basically a matrix where the entries aren't matrices, but what we've done is we've sort of compactified this matrix A into sort of these smaller sub-matrices, A11, A12, A21, A22. And so this can sometimes be useful when wanting to talk about sort of a larger matrix but wanting to split it up in a certain way, or if we kind of already have these matrices and there's a way to put them together. Sometimes using this block notation is nice. I claim we've already worked with it a bit when finding a matrix inverse. But so, probably best to see it as an example. So, we've defined A in this way. This means that if we defined A like this, and notice I've got all of these submatrices listed over here, then as a matrix where I expand everything and look at numbers, A looks like this. And so usually if we define a matrix as a block matrix in this way, it's customary to use sort of lines to partition the blocks. And so notice the way this is defined, it's just you take each submatrix, so here A11, you put it in the location relative to where it should go in A. So you sort of draw lines that sort of block out where each block matrix is going to be. And then you fill each block matrix in according to the partitioning of A. So notice this is A11, this is A12, this is A21, and this is A22. And again, like I said, this can have uses when, like, say we know these four matrices, or there's some reason we want to partition it off like this. Remember, we've already sort of done something like this with finding a matrix's inverse, where we sort of partitioned that line down the middle to separate A from the identity and eventually, A from its inverse. So we've worked with block matrices a little. So let's do B just for the fun of it. So let's say B we define in the same way. Pause the video, try it for yourself, try and set up B, sort of arrange the blocks in that way. All right, so B is equal to the following. Yeah, just like A. So, we have operations we can do with block matrices, and what's nice is the way that the normal matrix operations work translates very well to how block matrices work. And so what I mean by that is that basically notice, like, by the way we're defining this, these are almost sort of like, the block notation is sort of a matrix in its own right. And so we can end up working with these blocks much in the same way that we would have normally worked with regular matrices. So one question you might have had is, what is A plus B Well, we add block matrices in the exact same way that we add regular matrices. It's just we add the corresponding blocks together. So A plus B is a block matrix whose blocks are now A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22. And so we can calculate the exact dimensions of this, or the exact entries of this matrix. And thus, we have A plus B. So we can add block matrices together under some conditions, which I'll state here. You sort of might already kind of be able to see what the conditions are going to be. Certainly the way we've defined them, so like the definitions of the big matrices in block form have to be the same, and then also the dimensions of the individual blocks themselves have to be the same. And so we'll say component wise. So it's a lot of writing. I apologize. But so we say that two matrices A and B can be added together, and I say component-wise just like this. So we add the specific associated blocks together, and that's how we add block matrices. If the dimensions of the larger matrices themselves, when defined in block form, are the same. So here we had defined A and B as 2 by 2 block matrices, and the dimensions of the individual blocks that I'm trying to add together are all the same. So that is, all parts of the addition must satisfy the normal addition rules of matrices. That is, the dimensions have to match up everywhere. If so, we add it component-wise or block-wise, and this is how we do it. So we can also multiply block matrices basically in the exact same way that we add them, in that we're going to work with the blocks, and then what we're doing with the blocks sort of happens, we do it on two levels just like we do addition. So I figured we'd look at an example of that next. So multiplication is going to be done the exact same way. We're going to treat the block matrices sort of as normal matrices, multiply like we would, but then we have to do a second level of multiplication of the individual blocks. So this time we're going to define C1 and C2 like so. And we're going to define C sort of as this block, I guess, vector, right? But vectors are secretly matrices. We're going to define C as this block vector, and I'll show you how multiplication works. So notice if we were thinking about the block matrices sort of like in their general form, this is a 2 by 2 block matrix. This is a 2 by 1 block matrix, or just a vector of length 2. So normally I could multiply these. And remember, the way multiplication would work, I'd do my dance, and I'd get the following. Where here, this is a block vector of length 2, so a 2 by 1 matrix, whose block entries are defined by the following matrix products. So I have to calculate a few matrix products to figure out exactly what this is, but we can do that. So there's A11 times C1. So next, A12 times C2. Notice this is a 2 by 1 matrix multiplied by a 1 by 2 matrix. So this is a really weird type of matrix multiplication, but basically what this is just going to be is we take the first row of A12, match it up with the first column of C2. So that's just -1 times 2. Then -1 times -1. Then 3 times 2. And then 3 times -1. And that's good, right? Because if we're going to add these two matrices together, and, you know, kind of weird, but these two things are matrices, they should have the same dimensions. So that's A21 times C11. And that's A22 times C2. And my battery's running low. I have the charger here, though. All right, there we go. I won't lose power while I'm recording. So now we just put all of these blocks in their appropriate place. So here it should be the sum of these two matrices as my first block. And the sum of these two matrices is my second block. And that would be that. So this is exactly how you do block matrix multiplication. Again, it's a little involved, but I think sort of the main purpose here, and you know, you could always do this, like if you had smaller matrices like this, by just expanding everything and doing multiplication in the normal way. That's a completely valid option and maybe better, but like I said, sometimes it makes sense to do it this way. And we'll often call on this type of, I guess, sort of this type of arithmetic and this way of looking at things when we talk about other more general proofs that we're going to do later on in some of these sections. And so next, I want to finish with a fun problem of finding the inverse of a block matrix. And the solution to this problem will provide you sort of a method for some of the problems that you're going to do on your homework. So block matrix multiplication, done just like this. And we'll finish up with one more fun problem. So we have been given a matrix A defined as a 2 by 2 block matrix again. And so here I've got A11, which is an invertible P by P matrix, A22, which is an invertible Q by Q matrix, and A12 and the zero matrix, just rounding off the other two blocks. We're tasked with finding A inverse. And so what we want to do is, this is a little bit of a vague question as initially stated, but what this question is asking us to do is to find another inverse for A in block form in terms of A11, A12, and A22. And so I'll show you what that means. So notice that A is a P plus Q by P plus Q matrix. And so if there is an inverse to A, we should have an equation like the following satisfied. All right, so I will list what each of these matrices are. So this is the block matrix A. This is the block matrix A inverse. This is the identity matrix of dimensions P plus Q. And so notice that the identity matrix can be defined as a block matrix in the following way, because remember the identity matrix is just a diagonal matrix with all ones on the diagonal. Defining it as a block matrix like this just defines the P plus Q identity matrix. So what this problem is asking us to do, and you'll do something similar on your homework, is calculate B11, B12, B21, B22 in terms of the blocks of A in order to satisfy this equation. So the way we do that is we actually calculate each entry of the of each of these matrices one by one and figure out like what equations should be equal. And so I think it'll make a lot more sense if I just do it. So the first equation which has to be satisfied, well, a11 times a12 matched up with b11, b21 should equal the identity matrix. So this is an equation, or a matrix equation, which must be satisfied because this matched up with this should give me that entry. And so now I'm going to do the rest of this a little quicker. We should have 4 more equations that are satisfied. And I think what we'll be able to do once we write out the 4 equations is sort of work backward and solve for each one of these entries. So next we've got A11, A12 matched up with B12, B22. That equals 0. Notice we have a 0 here. Oh, nope, that's not equal to 0. That's equal to I sub q. So, 4 equations, 4 matrices. For this, we're actually going to want to start at the bottom. So notice that since A22 is invertible, and A22 times B22 is equal to the Q by Q identity matrix, the invertible matrix theorem tells us that B22 has to equal A22 inverse. So we've solved for one of our matrices already. Notice since A22 is invertible, I can actually multiply both sides of this equation by A22 inverse, and then 3 implies that B21 has to equal 0. So B22 is equal to A2 inverse, B21 is equal to 0. All right, so next, since B21 is equal to 0, well, this means that 1 implies, right? Since B21 is equal to 0 here, I know that B11 is equal to A11 inverse. So that's what equation 1 tells me. And so last thing I'm going to do, well, I need to solve for B12. This is not going to be quite as nice as the others. Well, so remember we know that B22 is equal to A22 inverse, so I can plug it in immediately. And now, since A11 is invertible, I can actually just solve for B12 in this equation. So first I subtract that term, then I'm going to multiply by A11 inverse. And so just like that, we can use our new knowledge of blocks matrix multiplication to solve for each of these blocks of blocks of A inverse in terms of the original entries of A, and maybe 0, in order to solve the problem. And so that's sort of, you'll be doing a very similar type of problem on your homework, but that's block matrices. You can add them, you can multiply them, and we can sort of use them, work with them sort of like a lot of the matrix operations in this way. So that will do it for, I guess, this sort of section 2.3, section 2.4 day. I apologize for making this video so long, but I figured this was easier than splitting this up into two this time around just because of sort of the nature of it. So yeah, thank you, and I'll see you in the next section.